Good morning. This is the first lesson of in our textbook of section 9.1a. It's a long lesson. I'm going to divide it into 3 parts. This first part, properties of radicals, I think we've already talked about. I know we did last year, but I'm going to do it anyway because it's really important. So the 2 properties of radicals that we want to talk about. And I guess even before I do that, let me talk about some vocabulary. The little number that tells you what root you're looking for, that's not there if it's a square root. Higher order roots is called the index. The number underneath this radical symbol is called the radicand. So we've got a radicand, we've got an index that says what kind of root we want to take, and that whole thing together is called the radical. The properties that we want to look at are the product property, which says if I have 2 numbers, and I'm multiplying under the radical, I can take those apart. If I start with them apart, I can put them together. So we're allowed to multiply square roots as long as the indices are the same, and provided that those numbers are both greater than or equal to 0. So the square root of 2 times 3 is the square root of 2 times the square root of 3, and that would be the square root of 6. We also have the quotient property that says if I'm taking the square root of a division problem, I can take the square root of the numerator and divide that by the square root of the denominator, as long as the number in the numerator is greater than or equal to 0, and as long as the number in the denominator is greater than 0. We use these all the time when we're simplifying radicals. And remember, square roots are, or any radical, is simplified as long as no radicand has a perfect nth root factor. So for these, no radicand has a perfect square root factor. No radicals contain fractions. So if it looks like a fraction, we've got to get rid of it. And it can never have a radical in the denominator. So no perfect square factors, no radicals in the denominator, and was the third one, and no fractions are left. So look at example 1. These look like the ones that we've done ever since Algebra 1. This is on, if you're following along with me in your book, this is on page 480, example number 1, right sort of in the middle of the page. The square root of 108. 2 ways to do this. There's the first way that you learned to do it, which is probably dividing by prime factors. And there's a more efficient way to learn how to do it, which is thinking of perfect square factors. So if I'm thinking of 108, and I think hard, I know that that's 36 times 3. 36 is a perfect square, so when I think of square root of 36, right away I think of 6, and then the square root of 3 is what's left, so 6 root 3. The way you probably started learning these in algebra, in pre-algebra, was to do the prime factorization. And then whatever this index is, that's how I'm trying to group them. So this is a square root, so that means I'm looking for groups of 2. So 2 2s and 2 3s means that I can take out of that radical a 2 and a 3 because I have a pair of each of those. And I have a 3 that's left behind. So it was 2 times 3 times the square root of 3, which is 6 root 3. If you can think of those perfect square factors, that is definitely the fastest way to do it. If I'm looking at one that has variables underneath the radicand, the same principle holds. So I'm looking at 9x cubed. 9 is a perfect square, so I'm thinking of it as 9 times x squared times x. Well, these are easy. Square root of 9 was 3. The square root of x squared is x, and that leaves the square root of x behind. If you're doing it by division of primes, 9 is 3 times 3. There's a group. X cubed is x times x. Times x. I've got a pair of 3s, so it can come out. I've got a pair of x's, so that x can come out. And I have 1 that doesn't have a pair, and so that has to stay underneath the radical symbol. Look at monitoring progress down at the bottom of page 480. The first one they gave you was the square root of 24. If I'm thinking of that as perfect square factors, I might think square root of 4 times the square root of 6. And so that would be 2 root 6 when we finished. If I'm looking at negative 80, I might think of that as negative. That negative sign stays on the outside. And I might think of that as 16 times 5. And the square root of 16 is 4, so this simplifies to -4 root 5. If I'm looking at 49x cubed, and I'm thinking of those perfect square factors, 49 is a perfect square, so I know that's going to be 7. X cubed is x squared times x, so 7x, and I have that little x left behind. And 75 n cubed, I can think of that as 25 times 3. And n to the 5th, I could think of that as either n squared times n n, or just n to the 4th times n. And when we simplify that, the square root of 25 is 5. I can't do anything with the 3, so I know that's going to be left underneath. N squared is n squared is n, so n squared. Or if I think of that as n to the 4th, the square root of n to the 4th is n squared. And I have an n and a 3 left behind, so left hand under that radical is going to be 3n. So when you finish, this one is 5n squared times the square root of 3n. We also want to look at example 2. So these were all simplifying using the product property. Example 2 on the next page in your textbook talks about the quotient property, or uses the quotient property, which means we can pull those fractions apart. The marker isn't erasing very well. So if I'm looking on, this is 481, the top of 481 in your textbook, which I had already moved to in my notes so I could remember what I was going to tell you. Trying to consolidate this. I hate to have long videos. They're even more boring than long classes, right? So quotient property, I'm looking at example 2. Example 2, looking at A, which gave you the square root of 15 over 64. Well, 15/64 doesn't really reduce, so let's pull it apart. Square root of 15 over the square root of 64. We know the square root of 64 is equal to 8. And square root of 15, no perfect square factors, so that is simplified, and we leave it as the square root of 15 over 8. If I look at the B example that went with that, that was the square root of 81 over x squared. Pull it apart. Square root of 81 over the square root of x squared. I don't have to write this on my paper. I can mentally pull it apart. I know that that's going to be 9 divided by x, as long as that x does not have any value equal to 0. If we look at example 3, they're using cube roots, and those properties are still, the same. So look at number A. This is example 3, using cube roots instead of square roots. Now I've got an index that's written. So I have the cube root of negative 128. So I'm thinking of that. Now instead of thinking of perfect squares, if you can think of perfect cubes, it will speed you up. So if I think of 128 as the cube root of negative 64 times 2, cube root of negative 64 is negative 4. So we have negative 4 times the cube root of 2. If I look at example B, the cube root of 125 x to the 7th, the cube root of 125 is 5. And I have two ways to do this. If you can divide 7 divided by 3, or 7 divided by 3, 2 times. 2 times 3 is 6, and I have a remainder of 1. So this is the remainder. This is the number that can come out. So this is the exponent of things that come out. So I have x squared. I have an x that's left behind. So this will be the cube root of x. If this is confusing, play the video one more time. I'm dividing that exponent that's underneath the radical by the index. So 7 divided by 3. How many times is that? 2. So that's the exponent for the variable on the outside of the radical. this is the exponent of the variable underneath the radical. Or if we don't like that, you can always divide by primes. I hope we don't have to do that for 125. So maybe that's 5. And x to the 7th, think of that as x cubed times x cubed times x. There's a group of 3, so I have an x that comes out. There's another group of 3, x times x squared, and an x left underneath the radical. That was the B example. If I'm looking at letter C, that was the cube root, and this time we have a quotient of y divided by 216. Pull them apart. So the cube root of y divided by the cube root of 216. I'm thinking, what goes into that? 2 and 1 is 3, and 6 is 9 goes into that. Also 6 goes into that. And it turns out the cube root of 216 is 6. So I end up with the cube root of y divided by 6. And the last one in that example was the cube root of 8 x to the 4th over 27 y cubed. Pull them apart, so you have the cube root of 8x to the 4th divided by the cube root of 27 y cubed. And then just handle each one separately. So for that numerator, the cube root of 8, I know that's 2. Cube root of x to the 4th, I'm going to have an x on the outside and an x left underneath. In that denominator, the cube root of 27 is 3, and the cube root of y cubed is just y. So when we finish, we have 2x times the square root of x over a denominator of 3y. Look at monitoring progress that is at the bottom of 481. You can either pause here and do them yourself and see how you do, or you can just stick with me and we'll wrap this up pretty quickly. From looking at number 5, that was the square root of 23 divided by 9. Well, that doesn't reduce, so we're just going to pull it apart. Square root of 23 over the square root of 9, which is the square root of 23, which is prime number, divided by 3, and we are finished, and that looks good. If I'm looking at number 6, where you have the negative square root of 6, negative square root of 17, I'm going to pull it apart over the square root of 100, negative square root of 17 over 10. Remember, it doesn't really matter where you put that negative sign. That's a negative fraction. So if it was out in front, I could put it in the numerator, I could put it in the denominator, or I could just put it out in front of the whole fraction, which is probably the best thing to do. 5, 6, and 7, square root of 36 divided by z. Pull them apart. So square root of 36 is 6, divided by the square root of z. That was z squared. We haven't gotten to that part yet, but it's coming up, over z. And number 8 was the square root of 4x squared over 64. Well, that's pretty keen. Square root of 4x squared is just 2x. And the square root of 64 is 8. Remember, it's a fraction. So you want to reduce, and you'll end up with x over 4, or you could write that as 1/4 x, whichever is the easiest to work with when you're doing it. So that was 5, 6, 7, and 8. Looking at number 9. Cube root of 54. So think of perfect cubes or divide by primes and do it. Cubes are the way to go. So if I think of that as 27 times 2, cube root of 27 is going to be 3, and then I have 3 times the cube root of 2 for your final answer. Looking at number 10, you have the cube root of 16 x to the 4th. Well, cube root of 16, like how can we think about that? And think of it as cube root of 8 times 2, so I've got a perfect cube there, And next to the fourth, I can think of as x cubed times x. And so when I simplify, the cube root of 8 is 2, cube root of x cubed is x, and underneath that radical are the things that didn't have a cube, so 2x times the cube root of 2x. When I'm looking at number 11, that one was the cube root of a divided by negative 27. Remember, as long as the indices are odd, we don't have to worry about that negative sign that's underneath the radical. That's only an issue if these indices are even. So when I'm doing this, I don't know what a is, it's the cube root of a. But when we pull this apart, the cube root of negative 27 is negative 3, and so my final answer is negative cube root of a over 3, or negative 1/3 times the cube root of a. And the last one for that monitoring progress was number 12. And it looked like the cube root of the numerator 25, c to the 7th, d cubed, all over 64. Well, the first thing to do is pull it apart. And so when we work with that, we have the cube root of 25 c to the 7th d cubed divided by the cube root of 64. That denominator is just, oops, not 8, is 4, and that's good. And up here we're going to see, well, what can we do with that cube root of 25? Any cubes? That's just 5 times 5, so nothing to do with that. How about that c to the 7th? So if I think of that as c cubed times c cubed, remember we're adding exponents when we're multiplying, times c, I can take out a c squared. Let's have a c left, I can take out a d, because d cubed, and so what I end up with is that cube root of 25. Nothing we could do with that. I have a c left with a c squared on the outside, all over 4. So c squared times d times the cube root of 25c, all over 4. I'm going to stop here. Your homework is the worksheets that are labeled 9.1a. I'm hoping this is a quick review, but I don't have your little faces to look, and you're not here to ask, and it's really important, so we're going to make sure we have this skill under our belts. So stopping here, 9.1a worksheets is what you're looking for. Talk to you next time.